Good evening, everyone. So welcome to week seven's talk from the Oxford Energy Society. Today, we're delighted to be joined by Professor Keith Bell from the University of Strathclyde. So Keith is a member of the UK's Climate Change Committee, and he's a chartered engineer and a fellow of the Royal Society of Edinburgh. He also holds the Scottish Power Chair in Smart Grids at the University of Strathclyde, and he joined Strathclyde having previously worked as an electrical engineering researcher in Bath, Manchester, and Naples. He is also the co-director of the UK Energy Research Centre, is involved in CIGRE, and has also advised the Scottish, UK, and Irish governments and the UK's Office of Gas and Electricity Markets on electrical energy and power systems issues. So today's talk is entitled Keeping the Lights On, Electricity Supply Resilience and the Transition to Low Carbon Generation. So we'll be looking at how interruptions to supply are kept to a minimum, digging into a couple of major recent disturbances and seeing how we can minimize such disturbances as we move away from fossil fuels. So I will hand over to Keith now, if that's okay.
Yeah, thanks very much, Saffron, and hello. Nice to meet everyone, even if I'll be relying on what comes through on the chat to get some interaction going. Yeah, in kind of usual style, I've got a whole bunch of slides to share. So let me try and find the right button to push. And which one is it going to be? Oh, probably that one, I think. Yeah, that's looking okay. Let's see if that pops up on everybody's screen, which it isn't quite doing yet. Why is it not doing that? Should be able to see. Okay. Oh, hold on a minute. Oh, here we go. Right, it's working. Great. So thanks very much, Saffron, from the introduction. And yeah, I mean, although I hold the Scottish Power Chair in Smart Grids, I mean, you can tell from listening to me that I'm not from Scotland originally, but I've been living here in Glasgow for 16 years now. Oops. So, bit of a wheel of something. Well, the system gets a bit confused. Okay, here we go. So yeah, I'm at the University of Strathclyde, which, in case you're not familiar with it, is in Glasgow. And of course, I guess you were familiar with Glasgow as being the centre of the world at the beginning of November, when we hosted the 26th Conference of the Parties under the UN Framework Convention on Climate Change, which was, I mean, really exciting for the city, really exciting for the UK to be host of the COP. And if we have time later on, we can pick up on whatever things came out of it. And I was fortunate, privileged to have access to the Blue Zone in the first week there. But yeah, University of Strathclyde is in the city centre. It's been around a long time, actually. So there was this chap, John Anderson. He left the University of Glasgow in order to found a place he called a place of useful learning in 1796. So that can give you a hint of what he thought about the University of Glasgow and its relationship to useful learning. I couldn't possibly comment on whether it's the same now, and whether my friends at the University of Glasgow do useful things or otherwise. But now, Strathclyde, we're proud to be one of the biggest universities in Scotland, and one of the UK's leaders actually in terms of engineering, technology, and business studies in particular, although also with other physical sciences, humanities, and social sciences. Okay, so what am I going to talk about in the next sort of 35 to 40 minutes? I've got too many slides, as often happens, so I'm going to go quite quickly, but yeah, we'll see how we get on. So just a primer, really, first of all, on operating an electricity system. And then, as Saffron said, I'm going to dig into a couple of events that you might have heard of. There was something that happened in Britain in August 2019 and in Texas earlier this year. And then what can we learn from those events? And, how should we approach system resilience or security of supply as we continue to decarbonize the electricity system? What challenges does that raise? So why are we interested in a power system or an electricity system? I mean, okay, it's because it's really important. So much of modern life depends on it, especially in terms of information and communications technologies. It's been in the vanguard of decarbonizing use of energy as a whole. Emissions intensity from electricity production has halved over the last sort of 15 or 20 years. We've now got a challenge of decarbonizing use of energy in heat and transport. And a major way in which we're likely to do that will be through electrification of those uses of energy and then continued decarbonisation of the electricity system. But a power system is a single, complex, non-linear, dynamic system. And when it goes wrong, it can go very wrong very quickly. And it's exposed. We see overhead lines, substations out there affected by the weather. Obviously, variable renewables dependent on the weather are affected by the weather as well, wind and solar and hydropower as well. We can store water, but only up to a certain amount. And experience from around the world tells us that recovery from what I've written here is a major unreliability event, a regional or a whole country blackout is pretty hard. I mean, interruptions to supply do happen. Fortunately, normally they're very localized. But these kind of big events, it's quite a difficult process to get the system back up and running. So we want to avoid it as far as possible, and not just because of the inconvenience that's caused in the meantime. Now, a power system comprises all of these different elements, and these got to be coordinated and hang together in a stable way. The sources of electricity, the transmission network at high voltage that carries the power across the country or indeed across continents, the distribution network at lower voltages that steps down the voltage and connects into individual properties and businesses. And we've also got some replenishable energy stores. I mean, hydropower, pumped hydro is the kind of most obvious one. And as we get electric vehicles connecting, that will there be other energy stores connected to the power system. And of course, there are various loads. The things we do with electricity, heating, already a certain amount of heating, lighting, appliances, communications, and so on. Now, we have to keep the system stable. We have to keep it within stable, safe operating limits. A lot of it is to do with safety. For example, faults can happen, whether due to lightning strikes or mechanical failures that lead to short circuits or equipment faults. So if those short circuits persist, the system can become unstable, but it's dangerous for anybody who happens to be nearby. So we need to make sure that faults can be detected quickly and that the affected bit of equipment is isolated quickly and safely in order to leave the rest of the system, hopefully, to continue to operate in a stable manner. What does a stable manner mean? Well, a lot of the generation equipment is only designed to operate at a certain speed. It's rotating in synchronism with the alternating current. So we've got to keep that frequency of the system within certain limits. We talk about a 50 hertz system, but it's plus or minus 0.5 hertz in this country, at least in terms of how the rules are written. It can survive a bit wider than that. A conductor carrying a current, it gets hot. We can't let it get too hot. The insulation might break down, inside a transformer, or a conductor expands, the air gap kind of gets closed. You get a risk of a flashover, a short circuit fault, and then you're into all those other problems again. And all these kind of, it's electromechanical system with rotating bits of generation plant, big physical bits of steel rotating. We've got to make sure that is kind of, synchronized with the rest of the system. Don't let it, lose synchronism and kind of its speed to run away. That becomes a bit scary, these big bits of metal rotating at more than 3,000 RPM. Now, what happens if we don't respect these limits? Well, if you have too much current, okay, you've got a bit of time. The conductor doesn't sort of expand immediately. The insulation doesn't sort of get up to a critical temperature immediately, but you've got to do something to reduce the loading, reduce the current in order to reduce the temperature again. Voltages we need to keep within limits. That's another kind of complex aspect of the system about the kind of the angle deviation, the fact that the voltage and the current are not perfectly in phase with each other. So the phase difference, we talk about reactive power as being a kind of a proxy for that. So we've got to kind of manage that and keep everything kind of balanced and stable. So that means keeping voltages within limits. We talked about instability. And if you get it wrong, you disconnect some loads and then you end up, even within seconds, potentially blacking out an entire country. Now, we know that, okay, I've just said we've got to keep all this balanced. So the 50 hertz, the system frequency balance, that's a product of, how much electricity we're producing versus what the loads are, how much we're using. So you've got to keep the generation and the demand balanced at all times. And that's difficult because the demand for electricity changes all the time, and especially on a kind of daily cycle. And there's another cycle you can recognize through the week. Working days are different from weekends, and then you can see a pattern through the year. Obviously, this time of year we switch the lights on quite early. We're using heating in the summer. It's not the same. So anyway, so this is one of the challenges in operating an electricity system. We've got to get this balance right about generation and demand across all time intervals. And yes, storage can help us to balance things. Otherwise, you've got to bring on the generation at the right time and then take it off again, because a surplus is just as bad as a deficit. And then we've got to manage things spatially, so the generators are not where all the loads are. We've typically had a north to south power flow in Britain. Years ago, that's where the coal fields were in the north of England and in Scotland, using the coal, locally build the power station where the coal is and then move the electricity rather than move the coal and put the power station next to the electrical loads. And nowadays, all the best places for wind power tend to be in the north as well, because the average wind speeds are higher. And we're now putting, obviously, lots of wind farms offshore. So the network is really important to getting access to these resources, but we've got to avoid overloading the network. And sometimes if you put too much loading on the network, not only do the conductors get hot, but you risk some sort of instability. But actually, if you do interconnect all these different areas, now you start to get a choice about the sources of generation. You can use wind power when it's available, or you can institute a market and have competition among sources of electricity. And hopefully that competition brings benefits in terms of reduced prices. Although, okay, we've seen very high prices, mainly driven by the gas market in recent weeks. There's a lot of words on this slide, sorry, but maybe they'll be useful to look at more slowly afterwards. But the basic point here is that the physics of the system determine whether the system is stable and can be operated safely, and whether we can meet all of the demand for electricity. But then we can have an energy market. Certainly we've had that since 1990 in Britain, and different forms of market in other parts of the world as well, to help us utilize the different resources. But we've got to now marry these two together. The market has to be compliant with the physics. We might change the market rules, we can't change the physical rules. And there are always sort of delays and imperfections in market responses and various uncertainties. And we have a system operator who's given responsibility for trying to make sure they resolve all of this. So how do they do it? Well, they use various things that are called balancing services. So basically it's redispatching generation, increase it or decrease it to kind of get that balance with demand correct. Different sort of technical features, I suppose, to enhance stability, to help to manage voltages. So a lot of these things are automatic, but others have to be bought, scheduled. And there are different markets operating kind of day ahead, within day, 6 months ahead in terms of tendering for different services. And yeah, just a little note in there. So when demand exceeds generation, in effect, the electrical demand extracts kinetic energy from the rotating plant, which means that the system's frequency falls. On the other hand, if generation exceeds demand, because the electrical load isn't using all of the energy coming into the generators, that puts extra kinetic energy into the whole system. So it all kind of tends to speed up. So you can watch system frequencies, whether it's above 50 hertz or below, to see whether you're in balance or out of balance and in which direction. And you've got automatic controls that can correct that. Now, I said already that the system is vulnerable to disturbances. So there are, in particular, faults on overhead lines. Overhead lines cover a lot of kilometers, so there's a lot of exposure there. There can be high winds, the conductors get a bit close together, you might get a flash over between them. Lightning strikes is the most obvious cause of an electrical fault. It could be just equipment damage. The insulation breaks down over time for some reason inside a transformer, for example, or inside a cable. So you get about, on the transmission network, that's at 275 and 400,000 volts covering the whole of Britain, we might get 600 or 700 fault events on the network each year. Now, it's not kind of evenly spread. During storms, the fault rate, the number of faults kind of per hour, is around about 1,000 times what it is during kind of calmer conditions. But yeah, you get a feel for the number of faults. So how come we get all these faults? How come we don't get losses of supply? Well, actually, a lot of the causes of loss of supply that we would experience, lose supply to our home or whatever, out in the city centre or whatever, are caused by faults on the distribution network. Now, if it's during a storm, when there's physical damage is caused, then the repair takes quite a while. And that has to be managed carefully. Now, interesting here, I think this is from Christmas 2013. Some sort of blizzard conditions that affected the north of Britain, and Scottish and Southern Energy up in the Highlands was particularly affected by it. Interesting how the Department for Energy and Climate Change, the forerunner to BEIS, the Department for Business, Energy and Industrial Strategy in the UK government, did a review of this and a report, and they thought the distribution network operators did okay in restoring power, whereas the electricity regulator Ofgem thought that they didn't do okay. So how good is good, or what would we expect in these sorts of extreme weather conditions in terms of restoration of supply? Yeah, so our experience, as I say, is mainly at a distribution level, when this is the average, 80 minutes of loss of supply per customer per year, and the interruptions might add them up. So that maybe on average, bit less than one per person per customer, per year. If you're in rural areas on a kind of long stringy bit of network, you're more vulnerable to this than you're in an urban area where everything's undergrounded, and you've got also kind of backup supplies where a switch can be closed and you can be resupplied from another substation. The transmission network, I mentioned all this kind of 700 fault events, but very few of these, 20, 30, 40 a year, lead to loss of supply. Now, the point about the transmission network, if that does happen, it's quite a lot of energy that's not served for that particular event. But if you think about how much energy is carried in total across the transmission network, then the proportion of energy that's not supplied is very, very small. In other words, by that metric at least, the transmission network is extremely reliable. But okay, you might experience a loss of supply down at the distribution level. And it's a kind of question of scale. I mean, there's some analysis by a chap called Ian Dobson over in the US and some colleagues of his a few years ago that noticed a kind of log law in terms of the energy that's not served due to faults and the probability of that amount of energy not being served. And that's kind of a function of the design of the network to a large extent. So the transmission network is designed such that a single fault event won't cause any problems. You've got enough kind of redundancy, spare capacity on the network, and in the ability to control things like voltage and whatever, that mean that, it's not a problem. Okay, if another fault happens after that, before you've had a chance to kind of re-secure, to kind of redispatch things and make sure you are kind of safe against the next event, then you might have a problem. So it depends on how quickly these faults are coming. Whereas it's just a kind of economies of scale thing. The distribution network is only, bits of it only serving a small number of users. Is it cost effective to put redundancy there? Have, two separate connections into every house? It's starting to get quite expensive. Would we all be willing to pay for it? How much would we pay for a more reliable connection than we've already got? And when you ask people that question, and you come up with a value of lost load to try to drive the kind of economic appraisal of design of the network, it looks like we're not far away from the right answer in terms of the design at the moment. But as I say, at a transmission level, if you don't manage to keep the system stable, then you could lose the whole country. So a lot of this is, the design and the operational practice is motivated by surviving these disturbances, these random faults that happen due to the weather or equipment failures. The first thing, of course, is simply, is there enough generation to meet demand? So we've got to do the scheduling right. In the longer term, we'd be worried about how much generation capacity there is. We've got to make sure enough of it is built. We've got to be concerned now, of course, about the variability of power from wind turbines and from solar PV panels. And then we've got to get the power from the generators to the load. So we need enough network capacity. And then this particular thing about how the whole system responds to faults. And the controls that are in place. And so all of this kind of challenge sort of managing disturbances. It's kind of, the first level, preventing any interruption if we can, so that everyone's supply is continuous all the time. If we can't prevent an interruption, at least we contain it, so there's not too many people disconnected, and they're not disconnected for too long. And then if they are disconnected, we've got to be able to get their supply back again as safely and quickly as possible. And there are, like I say, there's all sorts of things I'll come on to and touch at the end about what sorts of things we use to do that. So the stability of the system is a particular challenge. And again, I'll return to that in a few minutes. So as I say, stuff happens. Normally, it doesn't cause a big problem, or the problem doesn't last for very long. On occasions, it does cause a slightly bigger problem and gets a lot of attention. So there was an event, you might remember, back in August of 2019, that my family laugh at me because I talk about it so often. But I think it tells us a lot, as the power system engineer, about how the system is behaving and how it's changing through time. And this generated a whole load of headlines, none of them really very favorable about the industry as a whole. And of course, it generated attention within the government and with the regulator. So some people were jumping on this and trying to claim that this was proof that you can't rely on wind power. Actually, that wasn't the case. That wasn't a specific problem. It wasn't to do with the variability of wind power. There was something about the way a particular wind farm had been installed and commissioned, but that could be of anything that's not installed and commissioned in the right way. It wasn't sort of a feature of wind power as such, as I, among others, tried to say in the press. And this was a statement I put out, picked up by some newspapers who said wind power not to blame, says professor. In the Scotsman, they were proud to say, says Scots professor, which got a particular reaction from my daughter that maybe you can see on the screen there. So what happened? There was a lightning strike on a particular overhead line. Now, lightning strikes happen on the transmission network, I don't know, tens of times a year. They don't normally generate headlines. In this case, for a reason that is still not fully explained, actually, it triggered the loss of a lot of power from a very large wind farm at Hornsea, which is just sort of off Humberside, and from a fossil fuel generator at Little Barford, somewhere in sort of the south centre of England, if you like, a combined cycle gas turbine. So I haven't heard at all why the Little Barford turbine tripped. The investigation conducted by the government and Ofgem didn't reveal any answers to that. There were some suggestions about what happened at the wind farm, which was basically a wrongly specified control system that they were able to update the following day to something that was more correct. Now, these combined within a few seconds of each other led to this imbalance. Now there wasn't enough generation to meet demand. Now, normally there's spare generation, spinning reserve there to kind of cover some shortfall like that, some sudden loss of infeed. But these two things together exceeded the amount of frequency containment reserve that had been scheduled. So that was being used, but not enough to arrest the fall in frequency and restore that balance. That frequency containment reserve would increase its output automatically. Now, because of this large kind of almost simultaneous loss of infeed that exceeded the frequency containment reserve, the system frequency fell very fast with a very high rate of change of frequency. So you can see the kind of green line there that is measuring as a measurement of the rate of change of frequency. Now, being a kind of derivative signal, it's got a lot of noise on it. The frequency fall you can see in the red line. The dotted lines is where one of the researchers in my group, Callum McKeever, managed to reproduce the event in a quite a detailed simulation. In fact, he reproduced it more closely than the system operator did. To be able to use that to study what happened, and also subsequently how things might have happened differently. So that high rate of change of frequency, that triggered the loss of some small scale generation that had particular protection that was triggered by a certain threshold of rate of change of frequency. So that made the whole thing worse. You've lost more generation. And there was other small scale generators that were lost as well, using a type of protection that the regulator had said is not allowed to be used, but they hadn't got round to disconnecting it yet and replacing it with something else. So that added up to a much bigger loss of infeed than we're accustomed to managing. There's always a risk judgment to be made here. what's likely to happen and how much do you carry to kind of limit the impact of it. Anyway, things kind of happened subsequently. Then another unit, a little Parford, tripped, and it got to so low, the system frequency, that it at 48.8 hertz, to save the system, you've still got this imbalance between generation and demand. If you haven't got enough generation to ramp up its output, the only thing you can do to restore the balance is to get rid of demand. So here was some low frequency demand disconnection that did what it said on the tin and disconnected automatically some demand, some electricity use. And that was the thing that got a lot of the attention, really, because now it's an interruption to supply, and it included supplies to I think some signaling, and even the frequency deviation. Some particular trains in the southeast of England didn't like it. They had some particular settings of their own controls that just switched themselves off. Now, the investigation afterwards revealed that really shouldn't have happened. It was a kind of, I don't know, in my opinion, a bit of a sloppy kind of specification. But then it turned out that rather than being restartable by the driver of the train, a technician had to come out with a laptop and plug it in to get it restarted. So you had now this hours of trains blocking the line in big parts of the southeast of England. Okay, if you're interested in finding out more of that, there's a particular article that Callum and I and another colleague, Marcel, have published recently. Okay, so that was a load of kind of dynamic stuff and a few unfortunate things that coincided. Another event was from February this year in Texas, and lasted for a few days due to an ice storm. So in this part of Texas, very unusual to get that kind of cold weather. I mean, really cold. And because it was so cold, actually, a load of the generation plant, which should have been burning gas, failed to operate. So they lost a lot of that generation and couldn't meet the demand. The demand, of course, was higher than normal because a lot of people had switched on electric heating. So it ended up that 20 gigawatts of load was disconnected, affecting 4.5 million customers. Now, the Texas system is kind of interesting. It's its own system. It's not interconnected with the rest of the US. I mean, kind of classic Texan style. And electrically, it's a similar size to the GB system, actually. So, 20 gigawatts of demand here would be, this time of year, this time of the day, would be about a third of the whole of Britain's electricity demand. That gives you a sense of the scale of this. Now, a big part of this was due to, failure of generation. So a generation inadequacy is what we would call it. It's not enough to meet the demand. But a big part of it also due to distribution network failures, just a kind of accumulation of ice, a mechanical failure of these kind of low voltage overhead lines. The system operator in Texas, ERCOT, said that they were 4 minutes and 37 seconds away from a complete collapse of the Texas electricity system that they then said would have taken months to fully restore all the demand. I mean, that is just astonishing and astonishingly bad, and lucky that they didn't get to that point of no return. And we can see how that kind of event developed over time. As the bad weather came in and things started getting colder, electricity demand increased, certainly relative to what you would normally see on a Sunday afternoon. And then, so that's the black line of demand. And the red line a bit lower down is the unavailability of generation. How much plant, how much capacity in terms of gigawatts is unavailable. And the red line going up as plant becomes unavailable, a lot of it. And that was the reason why the system operator, just to maintain the balance, was forced to start disconnecting demand. So the black line falls. And eventually you kind of get back onto more of an even keel. And I'm looking a bit more closely at, I've mentioned already, one of the ways of seeing the imbalance or the balance between generation and demand is system frequency. They're aiming at a 60 hertz frequency. So it always wanders around a bit, but you can see it falling as the generators fall off, and the system operator getting desperate in the kind of red text there, ordering the shedding of load, the disconnection of electricity customers. But the frequency kept falling, and they kept having to order more disconnections. and the normal kind of lower threshold was breached. If they'd stayed there, this is it, you see. So the various generators, I don't fully understand why they were specified in this way, but apparently if the system frequency was below 59.4 hertz for let's say for 9 minutes or more, they're allowed to disconnect themselves. So you've already got a shortage of generation. It's now going to be made worse. So that was the situation where they were close to things suddenly becoming a hell of a lot worse. And you can see the accumulation of generation outages there in the chart on the left, and how many of them were weather related. I mean, there's always some, well, often some unavailable, I don't know, doing maintenance, or there's some equipment faults. But here, a whole load of outages that were said to be weather related. And the other thing that this did, as you get a shortage of generation, the spot market price, the wholesale market price, soared up to an administrative cap of $9,000 per megawatt hour. So normally they would have been trading at, a few tens, 50, 60, $70 a megawatt hour, similar to what we have in Britain, actually. Normally, average electricity price in the wholesale market is about, 45, 50 pounds a megawatt hour. So this is huge. And if you're on the sort of contract that is exposed to these very high wholesale market prices, like a kind of real-time tariff, then you're suddenly facing a massive bill. So I don't know quite how this man Dallas TV spoke to managed to have a cost of 17 grand. There was some speculation he was growing some particular plants in his loft or something. But this particular retailer, I mean, we've seen retailers, electricity suppliers going bust in recent times in Britain. So this particular one offered this variable rate tariff, and they offered it at a particular monthly membership fee. So suddenly they're spending all this money in the wholesale market, and there's no way they're going to cover that cost from their customers. So they went bust. I'll load more words here, but there's another electricity cooperative that went bust, citing a $1.8 billion bill from the electricity system operator. This was stuff that Brazos was supposed to pay to the system operator as the administrator of the wholesale market. So what can we learn from all this? Well, that kind of August 2019 event in Britain, one of the things that affected it was the small-scale generation, distributed generation, which means it's connected to the distribution network, or DG for short. There's a lot of it. We think that our peak demand is about 60 gigawatts. We now have more than 37 gigawatts of this small stuff. I mean, we might think of solar PV on people's roofs, but there's also small solar farms dotted about, small wind farms with a few turbines, the odd turbine in a farmer's field, also combined heat and power plant, waste to power, municipal generation plant. All this sort of stuff adds up to this 37 gigawatts. And this might seem a bit shocking, very little of it is monitored and controlled. So actually, in the investigation of that event, the system operator couldn't say for sure how much of it was operating and how much of it was disconnected. Now, the distribution network operators historically have just basically been asset managers. A fault happens and they fix it. And if someone new wants to connect to the network, they design and install the assets to do so. As we're getting more of this generation on the network, and we're getting things like electric vehicles and electric heating, we want to make optimal use of the network's capacity, which means we do have to kind of do what the transmission system operator does and be more active in kind of flexing generation to match the network's capacity. In other words, to become a more of a distribution system operator, not just an owner of the network and maintainer of the assets. But their ability to do that, I think, was not shown in a good light because they had so little knowledge of what was actually happening. Another thing which we could see from the wind turbines was the use of power electronics on the system. This has been happening in the last, since the 1980s, really. But as power electronic devices have become capable of supporting higher voltages and larger currents, so you can use them in control equipment. I mean, the kind of devices that we use on laptops and things, we have solid state electronic devices to do the conversion from the AC power to the DC power that we need. This is kind of the same thing at a larger scale. It gives you a lot of flexibility because you can control these switches at, a few kilohertz of switching if you wanted to do all sorts of things, provided you know how to define what those sorts of things are. And this is the problem with the control system at Hornsea Wind Farm. It was not defined in a way that was good for the system. And we're getting more of this stuff. I think it's becoming a bigger challenge to get them to operate together in the right sort of way. And just as better collection of data to understand the risks. I've kind of already touched on that. And then also, who's responsible for managing how the whole system hangs together? There were things that happened on the distribution network, things that happened on the transmission network, things that were dealt with or caused by generators. These are all owned and operated by different companies. Who's responsible for what? Again, I don't think it was really all that clear. It revealed weaknesses in some of the processes, I think. And in Texas, they talked about this being an unprecedented winter storm, and couldn't possibly have seen it coming, therefore couldn't possibly have prepared for it. Well, actually not. It turns out there was a very similar event in February 2011. And I've got a whole load of words here from this report, so I'm not going to go through them all. But yeah, a lot of similarities. Cumulative loss of 30 gigawatts of generation capacity, spot prices hitting the cap that existed then, which was $3,000 per megawatt hour. Big problems with the gas system. Now, Blackstart units, they're really important because if the system did collapse, the whole system went black. You're trying to start it from nothing. You need a particular capability to do that. And a lot of these units, apparently back then in this 2011 event, weren't available. So if the worst had come to the worst and you collapsed the whole thing, you weren't going to restart it very easily. Problems with the gas system, things that were freezing, maintenance staff couldn't get there because the roads were icy. The electricity system affects the gas system because the gas system needs electricity supply for various kind of pumps and valves and things, as well as the electricity system is affected by the gas system because it depends on it for the source of electricity. So a big thing here, winterization, as they called it, had not been done to make sure that these things could still operate at very low temperatures. So a big recommendation was made there, and again, I look at the bottom here. States in the southwest, so it wasn't only Texas, should examine whether generators or operators ought to be required to submit winterization plans, and these states should consider enacting legislation, basically to oblige it where necessary and appropriate. This was 2011. And it turns out that those things were not done. Legislation was not introduced. Now we're calling it weatherization, was not implemented. And the Texas Senate had some emergency debates about it. Actually, to be honest, I don't know if they have since passed bills to oblige weatherization. But they did quickly pass a bill to kind of retrospectively suspend those very high wholesale market prices. And of course, the bottom line is that this affects people. And in this case, in 2021, according to the headline, at least 57 people dying, mostly from hypothermia because the gas supplies or the electricity supplies weren't there to keep them warm. So how do we avoid such things happening again? Now, this is in the context of the very necessary process of decarbonising the entirety of energy use. And the Climate Change Committee gave advice to the UK government as part of its advice on the 6th carbon budget about this time last year. And some of the advice was specific to the electricity system and includes the recommendation to phase out the unabated burning of gas for the production of electricity. That is, if you're going to burn gas, you've got to capture and store the CO2, and recommended that phasing out by 2035, which is not far away when you consider that electricity generation assets for gas turbines and wind farms and such like are typically designed to last for about 25 years. Nuclear power stations designed to last for somewhere between 40 and 60 years. The UK government has accepted this advice, actually only quite recently, just over a month ago. So We're going to have to get rid of the things that we normally depend on for filling in the gap when it's not windy or providing a lot of the system services. Now, we can try to understand another part of the challenge about, to do with the variability of wind and the variability of demand via these curves. So what I've done here with the dashed lines is take the demand for electricity at each hour of the year and sorted it, not chronologically, but with the biggest on the left and the smallest on the right. Those are the dashed lines. Now, and these are some 2030 scenarios. The solid lines are where in each hour I've taken the demand and then looked at how much wind power is available, how much solar power, how much hydropower, and how much nuclear power, all low carbon sources of electricity, are available in that hour, and taken the sources away from the sinks. And we call this the residual demand curve. And that green line is a scenario where we have met the government's target for 40 gigawatts of offshore wind by 2030. We look to the left, because we can't rely on wind all the time, there's still quite a big peak residual demand to be met. But we look down to the right, and there are times when actually there's a surplus of electricity production. We've got to keep a balance, so we'd have to curtail it to keep that balance. That sounds like a bit of a waste. How is that going to affect the investment case for low carbon generation? Maybe people can be flexible in their demand and start to use that, because actually the prices could be negative in those hours. It's not just there's a temporal issue. Things do happen chronologically. We could have low wind speeds for quite a period of time. Here's a period from 2018 where for more than a month, the average wind capacity factor was only about 8.5% in comparison with, the year-round mean of between 25 and 35%. It varies year by year. We look into some of those 2030 scenarios in a bit more detail. The one on the left, the residual demand is negative all day. There's a surplus all day. On the right, there's a deficit all day. Now, we can be flexible with our use of electricity in terms of when we charge electric vehicles. Can we, if we've got enough thermal insulation in our buildings, we can switch on the heat pump early and switch it off late, that sort of thing, which means flattening that residual demand curve. But there's only a certain amount you can do with that. There's still a lot of energy demand to be met. During a wind drought, which in Germany I believe they call a Dunkelflaute, have we got the resources to do it? If we can't burn gas for generating electricity without capturing the CO2, how else are we going to do it? And this is where hydrogen maybe comes into the picture. When there's a surplus, using electrolyzers, make some hydrogen, store it, and then maybe burn it or put it in fuel cells to meet demand for electricity another time. Now, the round-trip efficiency is not very good, but maybe it's the only way cost-effectively to move energy from one period of time to another period of time. Okay, I'm running out of time, so I'm not going to dwell on all these things that I've kind of touched on already, actually. And how do we measure how much generation capacity we need? There's a need to, how flexible is the demand going to be really? What capacity margin do you need? And then if you have flexibility of demand, how long will it last before it starts coming back? Storage is the answer, isn't it, to all of this challenge? I love this slide that a colleague produced a few years ago, Simon Gill. The size of the block is proportional to the size of the energy store. If I was in the room talking to you all in person, I would ask for people to shout out with what these different boxes represent. But because I'm not, I'm just going to move on to the answer, where actually pumped hydro storage that I mentioned earlier is just a tiny square there on the right. All of these other stores are actually fossil fuels that when we decarbonize the whole energy system, we won't have anymore. So we've made use of the storage because, a pile of coal, you can put it into a crusher and put it into a coal-fired power station at the time when you need it. You can store the pile of coal. You can store gas in pipes or in a tank and use it when you need it. It's not a two-way store, but it's still a very useful store that we won't have. You need the network capacity. There's all sorts of these technical things I mentioned earlier, so again, I won't dwell on it. But a lot of these technical things have been provided by fossil fuel generators that are going to close. How do we run the system then? I mentioned already these distributed resources, DG, and the fact that it's not at the moment monitored, and we're going to need, if we're going to, make best use of it and best use of the distribution network's capacity. There's a lot of money involved in upgrading it. Let's try and only upgrade it when we need to. We're going to need much better IT systems with lots of data and better models. And we need investment to get all of this. Are we getting the right investment signals such that we end up with a system that can be operated in a resilient manner? And all these things have different characteristics. They last for a certain period of time. You can flex them up or down if it's windy, for example, but it doesn't persist, not reliably. So there's no perfect, silver bullet to all of this. And but there's also stuff you can do on the network that isn't just about a source of energy. And again, what sort of investment mechanisms are going to encourage provision of the right mix of facilities? Do you leave it all to the market? Some people believe you should. Everybody just expresses an option. How reliable do you want your electricity supply to be? And let the market go ahead and deliver it. On the other hand, experience in the US, there was a lot of skepticism about the market. It was all left to the market there. So here's a chap, a professor at I think he's at the University of Washington or the Washington. I think it's a Washington State University, who I used to work with in Manchester, actually, Daniel Kirshen. He said, we have to recognize that markets have limits. They are not good at handling long-term decisions about infrequent events. And it's complicated by the fact I mentioned earlier. There's so many different actors in this space, and the relationships are governed by a whole set of, reams of codes and standards. How do we therefore, in this environment, ensure that everything is joined up? In this context, the various sorts of disturbances caused by all sorts of things. The sort of thing we can do is to do with the equipment, how you design it, also how you maintain it, as well as the decisions you make in terms of operating the system, which generators are you going to use at a particular time, and your ability to control things automatically. All of these things play a part in ensuring resilience. And okay, we could do some probabilistic analysis around parts of this as well. Who's responsible for all of it? There are all these different actors at play which feed into the need for these codes and standards to govern who does what. Are they going to invest? And these very different types of entities, established utilities that own a lot of the existing power stations. And there's challenges apart, people like Octopus and OVO who say, bring on the uncertainty, bring on the risk. That's what I'm good at. I'm employing lots of clever data analysts. I will manage these risks much better than my competitor will. So bring it on. Is this the kind of world we want to be in on the right-hand side? And did any of these parties bear the consequences of failure? Well, the energy user definitely bears the consequences of failure. Last few slides before I hopefully leave some time for some Q&A if we have any. Can you rely on the markets? Well, Mark Carney, former governor of the Bank of England, believes there are limits to the markets. In particular, an anti-fragile, resilient system requires banks that can stand on their own, which is why they are now required to hold 10 times as much capital as they did before the crisis in 2008. So maybe we need saving from ourselves. Perhaps the energy sector should be subject to particular regulatory standards analogous to the capitalization of banks, to do with, the storage of energy and the ability to use it. But who defines those needs? Today, we have all the various standards affecting different parts of the system. There's a new restoration standard actually been proposed by the UK government. If the system were to collapse, we should have enough facilities to bring it back within a certain period of time. But we have these questions need to be asked again because of the changing nature of the sources of generation, not just relying on variable renewables, but the technology is different. It is changing more now than it has done for 100 years. Okay, that's the end of my probably too long presentation. So I hope, even though I went through that very quickly, we might get any comments from anybody that's listening.
Yeah, that was great. Thank you so much for that, Keith. So we have had one question from Christina, which we'll come on to in a second. But just to note for everybody that if you have any questions, just to leave them in either the comments on Facebook or on YouTube, and then we'll be able to ask Keith. So I'll start with this question from Christina Rimkanete. So she asks, we used to have centralized electricity supply, and now we incorporate RES and transition to decentralized supply. How does this affect the probability of faults, and what would be the biggest challenges for TSO?
Very good question. So actually, the first thing is to say that it's not entirely decentralized anymore. So, okay, depends what you mean by centralized. So I'm going to assume, Christina, that you mean, kind of large-scale power stations connected to the transmission network. And, well, we've not always had that. That kind of became more of the trend through, I suppose, the 1920s and subsequently all the way up to, I guess, the 1990s, when there was still large-scale power plant was being built. Still a few things since then, but we still have large wind farms, actually, so it's still going on, actually, to be fair. The economies of scale dictate that big centralized stuff still makes a lot of sense, especially when you're going to offshore. But you're right, we do have a lot more small-scale decentralized supply of electricity. So on that event in August 2019, that was bad news, but only really, you could say, only because the sector had not kept an eye on what was going on in terms of how it was being protected and just monitoring and knowing what it was doing and making sure that everything was fine. So it did cause a problem. It's still a problem because those things have not yet been fixed, not fully. But is it necessarily a problem? Well, another way of looking at it is to say, well, if there are some network faults and you lose connection from your area to the rest of the grid, if you've got generation locally, why can't that be used to supply you? Why should you be entirely dependent on stuff being transferred from the other end of the country? So distributed generation resources could act to improve reliability, but provided they're controlled in the right way, the sort of stability of the little local system becomes the problem, not the bigger system. And the bigger system, you've got a certain diversity of sources and sinks, so things, kind of variations kind of average out. You won't have that benefit in a smaller bit of network. So yeah, it's a bit of both. A big challenge for the TSO. I think it is a big challenge to understand what all this stuff is doing and what the net effect is. So I think it does require, as I've said already, much more investment in sort of more widespread monitoring and control. So hopefully, Christina, that answers the question.
Thank you so much for that answer. So we've had another question from Paul Boone. So he said, thank you, Keith, very interesting. Do the seeming failures of the market price cap, twice in Texas and then recently in the UK, indicate that a carbon tax is a good idea?
Yeah, good question. So this is taking us a bit away from all the kind of engineering and physical behavior of the system into more kind of a markets question. So I guess one way of looking at it is to say that high prices are a necessary signal to ensure that the resources are made available in future. So, if you can only meet all of the demand all of the time if you've got enough generation capacity for the peak demand. But if the peak demand by definition is only reached kind of once a year, what's the demand look like in the rest of the year? So that low duration curve that I showed earlier kind of shows that. It never goes below a certain level and typically doesn't go above a certain level, but it spends most of the time somewhere in between, of course. So the generators, some of the generators are only going to operate some of the time. How are they going to recover their costs? From a reliability point of view, to kind of be able to guarantee meeting the demand, you probably still want them to be there, but you've got to meet all of their costs in doing so. So there's some people who argue, well, that depends on what they call scarcity pricing. The fact that in the wholesale market, prices can go very high, but only for a short period of time. So it encourages investment in new facilities to exploit those high prices, I suppose, but actually it enables them to cover their costs and still be there when you need them. So that's the other thing, is how long do high prices last? And so okay, if they seem to be, well, you might be vulnerable to market power, I suppose, if you've got very few last resort providers. The high prices we've seen here, I think, are a reflection of lack of capacity in the global gas market relative to demand. So in a way, it's the same phenomenon. People are desperate to get their gas. You've got two options: either just pay what is being asked or do without. And when gas is fundamental to keeping warm, it's very difficult to do without. So again, in a well-functioning market, actually you would see responses on both sides. On the production side, okay, there's a time lag to when new production can be made available, but hopefully it will be. Or on the demand side, meaning the demand for energy for that particular commodity will reduce because the prices are higher than you're willing to pay. We have seen that, actually. I think you've probably heard stories of, I don't know, what was it, a fertilizer producer, for example, that used natural gas, and they just went, the prices are too high, I'm stopping, it's not worth it. The price I can get for my fertilizer doesn't justify what it's costing me to make it. that actually then had a knock-on effect on some other parts of industry that were using the CO2 that was a byproduct. They haven't got supplies there. So, there's a whole set of supply chains where a choice not to use it feeds through. Now, if you really want the CO2, you better go and pay whatever the market wants. So then how are the market participants managing these risks? The fact that things can happen. And this is another feature, I think, of the wholesale markets globally. How well hedged are you? Have you got long-term contracts which guarantee a price and a certain kind of volume of supply? And how much are you exposed to the short-term variations? Now, there's a danger in taking a long-term contract that you realize you've paid too much and you could have got it more cheaply if you bought more from the short-term market. So then relative to your competitors who took a different kind of approach, you're losing out. So it appears that the various retailers that have gone bust in Britain had not been sufficiently well hedged. They had not gone out into the long-term market to buy their sources of electricity, and so then they're dependent on the shorter-term markets, where the electricity market is dependent on the gas market because it's using gas to generate electricity, and it's sensitive to the same gas market where the prices have gone up. So it's a risk management issue. How much can you manage that risk by having extra capacity, by physical storage capacity? Well, yeah, potentially you can do that. I think there was something in the news today about, again, the global oil and gas markets. I think it's various governments have agreed to they've got strategic reserves, physical stores of petroleum products. They're releasing those stores, saying, okay, we are now going to use them. It means you won't have those stores for next month, but you're making more of the product available in the market with the idea that will kind of bring the prices down. Yeah, we can then go into, well, why have the prices gone up so much? Why is there such an imbalance between the production and demand for gas? And it's something to do with the recovery from the pandemic. I kind of wonder whether the recovery of demand from that we're still not out of the pandemic yet, that demand has recovered more quickly than the production capacity, because some of the production capacity, there was sort of opportunistic maintenance on perhaps even mothballing of facilities. It takes time to unmothball or to finish off your maintenance and get the production back. Possibly also some geopolitical game playing in certain parts of the world as well. Very long answer to a question. I hope that was interesting, Paul.
Great. So we have another question from Hongyu Wu. Can you share your thoughts on the role of energy storage for short-term grid resiliency support, frequency support, power quality support, and what would be the market enablers in this case? Thank you.
Yeah, so another really good question. So, definitely there is a role for energy storage in short-term resiliency support. Absolutely, you're totally right. Already batteries are offering frequency support because, they can discharge or charge a battery quite fast. So that, the power rating on a battery is really important. As I say, they're already doing it. Actually, there was some suggestion in that August 2019 event that they didn't fully deliver in the way that they should have done. So there's a bit of the market mechanisms still need to be refined to give proper incentives to delivering when you're required. But anyway, there's a lot of interest in that. And I think it's a good thing. It's a good part of the mix. The market enablers, that is the big question then. There are other possible sources of frequency support. So for example, if it's windy, you want to use all the wind turbines. You don't want to have to displace them and curtail the output in order to use gas turbines that can provide this spinning reserve, this frequency support. Okay, so can't we get frequency support from the wind turbines? Well, the answer is you can, but the system operator doesn't like to do it because they're not sure whether it's always going to be there. This is back to a market question. When are you tendering? When are you writing the contracts for the frequency support service? If you're writing the contract a month ahead and you want something like a 99% guarantee that it will be delivered at the time, any time when you want it, a wind farm ain't going to be able to offer that. But if it's a few hours ahead, when they know whether it's going to be windy or not, then they could offer it. So that's an example of where actually I think there's a lot of market development to be done to enable some options. We could use batteries, but actually if you deloaded some of the wind turbines a bit, that might be cheaper than deloading a lot of wind turbines in order to bring on some gas turbines. The deloading gives you some headroom where if you need it to kind of respond to a loss of in-feed event, it can increase its output. So this sort of thing, I think we could be a lot more creative. There's another whole discussion there about longer term support, by the way, which is another thing, which I think is a massive issue that we're not really thinking enough about. And again, the market enablers for that. Anyway, I hope that helps on you.
Thank you. So it's come up to just past 6:30 now, but I know we have some unanswered questions. Are you able to stay on and answer a few more questions?
Yeah, that's no problem at all for me. Yep.
Okay, great. So yeah, we have a couple more that we can run through quickly. So
it's my fault.
Liam,
I did take too long on the presentation.
That's okay. So yeah, hopefully our audience can stay on for a couple more minutes as well. So we have from Liam, do you think future energy providers will be more actively trading on financial markets to hedge increasing volatility, or that they will be more hesitant to do so due to increased risk? He also said you mentioned Octopus versus the majors and the different potential outcomes, but he's curious where you think this will end up given all that we know today.
Yeah, so I mean, actually, the answer is that the energy providers already are the big ones have been for years actively trading. I mean, I don't know, it depends which financial markets you mean, but there are already different markets for energy, for electricity and for gas in particular, in our case, in terms of what we're talking about. Yeah, there are lots of different markets. According to some analysis I've seen from BEIS, the Department for Business, Energy and Industrial Strategy, now what is it? They talk about market churn. So how often a megawatt hour of electrical energy gets bought and sold before it gets physically delivered. And it's, 10, 20 times. So that just shows the kind of extent of activity in these various markets, from year ahead, month ahead, day ahead, and within day. And, there is volatility in these markets, and participation in the different ones is an attempt to hedge your overall exposure. And yeah, what I understand is that these suppliers that have gone bust it's suggested by people like Keith Anderson, Chief Executive of Scottish Power, that these companies didn't really understand these markets and were insufficiently hedged, exposed to too much risk. So then, in terms of to buy the energy that their customers want and need, they've only got, let's say, a fixed rate tariff for their customers. So their revenues are fixed, but now their costs are very much higher than they would have been otherwise. So, companies like, that's why I say companies like Octopus, I think they understand that it is a risky business to be in. And OVO. So I had a really interesting chat with one of the senior guys from OVO back before the pandemic, actually, when he was basically saying, yeah, bring it on. I've been going out and recruiting really clever people, clever data analysts, who I'm confident will manage the risk better than my competitors. And so long as I'm gaining business from my competitors, then my business will be succeeding. The other kind of approach to this, I suppose, which someone like Keith Anderson from Scottish Power and the other big six would be saying is, we're part of big businesses with big balance sheets. The retail business is just a part of the overall picture. If we end up losing money in the retail business for a period of time, it's okay. We'll still stay in business because we can absorb that across the bigger company. So, yeah, does this favor bigger players? Will we end up going back towards a less competitive retail market sector? It probably will. Will we strike that kind of happy medium between having enough kind of stability in the market while still having enough competition? I mean, you kind of rewind the clock, say 5 years, there was really minimal competition and minimal innovation in electricity retail. It was dominated by the big six. And it's only with companies like, OVO, Octopus, Bulb, who went bust yesterday, unfortunately, coming in and sort of disturbing them, coming up with kind of new ways of doing things and new ways of engaging with their customers, that they've kind of shaken it up. Was that an artificial thing? I mean, I can't remember now. I can't remember exactly the details, but there was a certain obligation that these smaller companies didn't have imposed on them. They only was implied when they reached a certain number of customers. So that was an attempt by Ofgem to get more competition into the market. It succeeded, but now we're seeing maybe a downside of that in terms of the way it's happened. I hope that sufficiently answers your question, Liam.
Great, and I think we have one final question from Clive, which is basically saying, when the gas or fertilizer runs out, what then? And he's also mentioned heaters, fridges, electric car chargers, they need to turn off when the frequency drops, and then a surplus causes the grid frequency to be allowed to go slightly higher to encourage flexible loads, etc. So do you have anything to say to that?
Well, it's all a kind of balancing act, so system frequency is a way we can see whether the balance is right in the electricity system. The problem with the electricity system is the time constants are very fast. You've got to do things quickly. There's very little inherent storage in terms of the charge actually of and the storage of energy in terms of the capacitance and the inductance of the system itself. Any of the stored energy around the electricity system is in the rotating masses or in the relatively small volumes of batteries. So our ability to kind of smooth out the variations by charging and discharging stores of energy is quite limited. The gas system has a lot more kind of room for maneuver. It takes a day for a molecule of methane to move from St Fergus to, say, London. You can store. There's a lot of what they call line pack, storage of gas within the gas network. You can charge it up to a higher pressure if you like. So certainly in the electricity system, we could widen the frequency bands. It's just a made-up rule. Somebody just decided I'll make it plus or minus 0.5 hertz. Other countries, it's got a wider band. In Shetland, it's an islanded bit of network. They're regularly wandering up and down between 51 and 49 hertz. The generation equipment is designed to deal with that. That's perfectly fine. Generation equipment in Britain should operate in a stable manner down to 47.5 or up to 52. So if you start saying, well, we're normally allowed to go plus or minus 1 hertz, your margin for kind of safety margin getting a bit smaller, I suppose. But if you design the equipment to deal with it, is it necessarily a problem? Especially when so much of our use of electricity is solid state and you're converting from AC to DC anyway. So you're trying not to let everything run out. Worst case, and this is kind of one of the big challenges in resilience, is containment, or another way of thinking of it is you want to fail gracefully in such a way that you can restart things. You also want the market to respond. Do I really need this right now? Do I really need, I don't know, whatever you might be doing with your electricity? Do I really need to charge my car right now? It's already got enough charge for an emergency dash to the hospital or whatever your kind of worst case might be. I don't need the battery to be full right now. I can wait till tomorrow. Or, I don't know, maybe you could turn the thermostat down. Just put a few extra jumpers on for a while. Okay, industrial process, there might be some kind of equivalent to that. But it's always been a kind of the holy grail of energy economists, electricity system economists in particular, to try to see more of a demand side response as the prices vary. And with electric vehicle charging, it could be at any time. Given the average use of energy, how much is stored in a battery, you don't need to have it plugged in all night. You could plug it in, but it only needs to actually be drawing a charge for part of the night. So there should be a lot more flexibility. If we've got well-insulated houses, we could switch off the heating for an hour, a few hours even, before we really start suffering. But yeah, we need to understand that much better, I think. And it just points to the fact that it's not just an electricity system challenge, the whole decarbonisation challenge. We have to think about the whole energy system and all of the things that we do with energy. So we don't want it all to run out. We want to manage the resources in the right sorts of ways. And as I say, that kind of partly involves investment decisions as well as operational decisions. If it does all run out, well, restarting the gas system is a big deal. A lot of safety issues, as I said already as well. Restarting the electricity system is a big deal. We would rather not get to those positions. I don't know if you can hear a cat meowing in the background. There we go. Maybe that's a good place to stop.
Sure. I think we've had one
Unless you
more
have any
question
other
come
questions,
through.
I don't know. I'm not in a big hurry apart from the cat.
Sure. Okay, so I think we have one more question.
Go for it. Let's go for it.
So from Karen, so what sort of markets do you think will emerge as a result of the transition to decentralized generation? And can you comment on whether you think local markets will form and what will they look like?
Yeah, so I was going to say there's no real obstacle to forming local markets right now. but in practice there is. One of the things about the kind of these retailers that are allowed to operate in the market, that any of us could choose what retailer to come from. A retailer could come along that's, I don't know, Oxford Energy retailer, and they're going to buy all their energy from, let's say, because you're very conscious about the environment and emissions, from wind turbines and solar PV panels in Oxfordshire. That's going to be what they do. And you could choose to buy your electricity from that retailer. There's nothing really stopping that from happening right now. I slightly hesitate because actually I think some of the kind of obstacles, there are obstacles to new retailers starting up. The license to be a licensed retailer is about 200 pages long. So you've got to work through and understand that and show that you can comply with it. I think I've not read them all. I've not read any of them actually, but I think a lot of the 200 pages are written from the perspective of consumer protection, safeguarding the interests of your customers. So, okay, apart from regulatory barriers such as that, where it's not impossible, it's just difficult, you can have local markets buying energy from lots of decentralized distributed generation. And some of those kind of trades do already happen. So yeah, sure. Why not?
Okay, great. So thank you so much for that. I think that's all the questions that we have. And thank you for staying on for a bit longer at the end as well. So thank you to our audience as well for watching. So thank you for all your questions, and keep an eye on our social media for our next event. So we have something Christmassy coming up towards the end of next week. So have a look out for that. And yeah, once again, thank you to Professor Keith Bell for joining us for that really interesting talk. And we hope you all have a good evening. Thank you.
Yeah, thanks very much, Saffron, and thanks everyone. And I look forward to meeting you in some other way, some other time.